Hi, welcome back. Right now we've got Chad Duffey, who's going to talk through Windows Defender Exploit Guard versus zero-day vulnerabilities. Thanks a lot, Chad, for being here and doing this. Over to
Perfect.
you.
Thanks for having me, Max. Hi, everyone. My name's Chad Duffey. I'm a security engineer at Palantir. And yeah, this talks about Windows Defender Exploit Guard and how it can help protect against zero-day vulnerabilities. The reason I wanted to give this talk is that exploit protection is built into Windows 10 and up, so it can offer significant resistance against zero-day vulnerabilities. And that is like, if you've got software that a motivated adversary is taking the time to develop an exploit for, and then they go and use that exploit in your environment, it might be that they find, or that you find, that it actually just crashes that application when they go and use it against you. What's actually more likely to happen though, not everyone has a motivated adversary targeting them. What's more likely is what we saw in some of the talks yesterday, where there are these exploits being bought and sold on the dark web. And it could be that you've applied exploit guard controls to your software, and so it actually fails in your environment while it's working in lots and lots of other environments. And you get that for free in Windows 10 and up. You can just tweak some of the controls, apply some extra protections, and it could be that an otherwise really reliable exploit fails in your environment, and you get some really good telemetry around that. So what I was going to do is not spend a lot of time clicking through, this is what it is, these are where you click, all of that. I was going to jump into some demos in just a second. But the thing I wanted to say first is that it is the next version of Emmet. So if you've dealt with Emmet before, it's the same thing, but Microsoft's done a great job of putting it into the OS, introducing a whole lot of other controls, and also just making it really easy to configure and really easy to understand the auditing and alerting and that sort of stuff. The point I wanted to make on this slide, though, is that it's super straightforward to get started. Like this afternoon, if somehow this tweaks your interest and you're like, wow, there's some software in our environment that I'm worried about that I think might be the target of things, or it might not be frequently updated, or whatever it is, all you need to do is click the start button, type the word exploit, and you'll go straight to that first screen shown on the big picture in this slide. And from there, you can actually just start tweaking your exploit guard protections on a per process level. You can apply them to the whole system. So the operating system says, like, you've got to have this particular protection for all the applications. But the way I recommend it is just to look at the individual program settings and start to protect the things that really present additional risk in your environment. The thing I wanted to say, though, is that it's actually really easy to turn this into logging mode. So even if you're not prepared to go and put, your really business critical applications and wrap them in exploit guard straight away after this short demo, one thing that you can do is you can just turn on audit settings, and those audit settings would allow you to say, like, for this particular application, this exploit guard control would have caused you a problem. It would have caused the application to crash. And that's the thing, like, I'll talk about towards the end, but that's the thing I'd encourage people to start with. So what we'll do today is we will start out with a real exploit against some real software. The software happens to be Stephen Bradshaw's Vuln server application. So it is deliberately vulnerable. It does have some vulnerable functions in it, but it applies equally to real vulnerable software. And I've included some links to real vulnerable software you can test the same approach with in the resources section. But what we'll do is we'll apply the mitigations after we've exploited the software. We'll look at how they are successful and where there's still some gaps. And then we'll go and apply a different approach to to the same software. We'll apply a different exploit guard approach and look at how it can help solve that particular problem as well. At the end, we'll briefly talk about the other controls because there's a ton of them. And the best thing to do is read the documentation on the Microsoft site. And then we'll just talk about the things that I got wrong at Palantir, because there was a handful of things that I thought I could just go and do that weren't quite the right approach for exploit guard, and we'll talk about that. All right. One thing I will mention is that I won't have time to talk about, like, how I found that I could make the application crash, which is a good first step as an exploit developer. That's called fuzzing, and it takes probably like one of the largest chunks of time in developing an exploit. But I put this link here like in big bold, just in case you want to jump ahead and see that. You could go straight to this link, and there are good examples to show you like how to fuzz this application, find that it has a vulnerability, and then go about exploiting that application. All right, so I'll switch to a demo machine. I'll try and slow my cursor down here just in case it cuts out. But what I wanted to show you is that we have some software running here. Looks to be just some client server application, and we have our adversary machine. And what we're looking to do is, first of all, we'll just prove that it's doing something. So we'll just use NC to make a connection to it. We know it runs on port 999, and we can just see like, this is a real application. It does stuff. We don't really need to care too much about what it's actually doing, because what we want to do is make this application crash in a hope that we can then redirect control of that application into some code of our choosing. And so what I mean by that is we can see it made the connection here. It did all the things. Let's look at a simple crash for this application. We worked out that this trun command, we did a small example of trun here. We just typed trun 555, but just zooming in really quickly here, you can see instead what I figured out is that if I create a string that's just a ton of arbitrary bytes, I'm just going to send the letter A, and then I append that to the trun command and send it over to the server, that probably this will crash. And let's give that a go. So we'll say Python crash. And what we'll probably find is that this will die, and that the application over here, oh, that's not good. Sorry. Try this again, Python crash. So hopefully the application has crashed on this side, and you can see that it has. What I wanted to show is what that looks like from the process perspective, so that I can demonstrate where exploit guard comes in. And so what I'll do, I'll just start the same process, but this time I'll start it inside the debugger. I'll just attach. We'll see it start up here. We'll just let it go. And so I'll just fire off the same thing. So all I'm doing is sending through a ton of A's to that trun command. And what we're finding on the application side is that that application crashes. And so what you can see down here is quite interesting. You've got an access violation inside the application. It's crashing when it's trying to get to an address. If you haven't seen this before, 41 is actually the letter A in hexadecimal. So from an exploit development perspective, this is super interesting, because as of right now, we've put arbitrary input onto the instruction pointer, or sorry, the instruction pointer is pointing to our arbitrary input. And right now it's all A's. This is rubbish, and that's why the application's crashing. It's not doing anything useful. But from a development perspective, as an adversary, this is great. And what's extra great is that if you look at the stack pointer, which is pointing to this 9C8 address down here, you can see that this is also our stuff. So we've got a situation where we're able to shove a heap of arbitrary input into this process, cause it to crash, but also cause it to crash in a way where we have control of the instruction pointer. And a common approach here is to then find an instruction that makes sense, that's already in the process. So I just happen to know, and again, this is in the resources section, how I searched for this instruction, but I happen to know that there's a useful instruction here. We can see that there's a jump to ESP. So you can imagine that instead of A's, if I was able to put this address, this 625011AF, into the instruction pointer instead of A's, what would happen is the instruction pointer would say, this is the next thing I need to execute, which is jump ESP. Well, if I jump to ESP, I'm jumping to that other arbitrary input. So you can imagine that instead of shoving A's here, if I shoved code into that, that big string, that buffer that I've sent into the process, I now have really good code execution inside this process. And I'll show you that real quick, and then we'll come back and look at how exploit guard makes this better. Let's just start the software, and let's let's create a listener. So I'll just do an NC NLVP on port 443. Actually, I'll do it over here so that we can see it, and I'll get rid of this for you. Sorry for all the junk. Okay, and we'll use our second script, and then we'll have a really quick look at it. You can see I've got code execution on that target. I'm on that machine, do whatever it is that I like. And the reason I can do that is we're able to further develop this exploit. Ignore this part for a second, but you can see that all I've done is I've figured out, instead of 3000 A's, if I send 2002 of them, and then I carefully put that address of the instruction that I want, which is 625011AF, and then I give myself some room with some no-op instructions. At that point, I can also send my buffer of badness through to the process. And in this case, it's just a reverse shell, a Windows reverse shell that I automatically generated with MSF Venom. So this looks very complicated here, but this is just automatic. It's part of, in Kali, MSF Venom's in there, and you can just generate this payload very, very quickly. There's nothing special about this payload is what I'm trying to say. But an adversary would usually choose their own payload. Like this exploit would be this part, and it would be up to the adversary what they put in their buffer. It might be that they instead choose to encrypt all your stuff on the machine. Seems to be very popular at the moment. The point I'm trying to make is that we've got a really reliable working crash at this point. Let me just move that out of the way. Sorry, I can see myself and I can't quite close this. That's better. I'm going to really quickly just show the software crashing again so that we can look at exploit guard helping it out. So I'll attach once more to our target software. I'll let it run. And rather than using the full exploit, I'm going to go back to the original crash because it's just a really good way to illustrate things. All right. So there are probably people on this call, I know there are definitely moderators on this call that understand that what I just showed you is very unlikely to work in a lot of environments. The reason is that this here, our arbitrary code, should not be executable. It should be readable, should be writable, but it's data. Like this is meant to be data. It's not meant to be code. And so when I redirected control of execution down here, this should have crashed. And it should have crashed because of a technology called DEP, Data Execution Prevention. And that's been around since Windows XP. So there's nothing exciting about that. And I'm definitely not trying to do a talk about DEP. I know that would be quite late in the game. What I am trying to show, though, is that DEP has got really good workarounds now. There's a thing called return-oriented programming. You probably see it written as ROP. And what that means is that adversaries have worked out that while DEP says I'm not allowed to execute this stuff right now, I can actually go and use Windows APIs to make that code executable. So the one I'm thinking of is the virtual protect. There is a function in Windows called virtual protect. Adversaries using ROP have figured out that they can call this. If I try and go down that rabbit hole in a 20-minute talk, I'm going to fail badly. But they've figured out that they can call use ROP to call virtual protect. They pass in a parameter that says page execute, and now they've marked that memory as executable. And then they can just use their payload as normal. They've worked around DEP because DEP's only designed to block non-executable pages. But the new thing in exploit guard is arbitrary code guard. And what that will do is if this function is called from inside a running process, it will return status dynamic code blocked. And that process would then crash because DEP would say, well, you didn't succeed in marking those pages as executable. So, hit the road. Let me just show you that really quickly because I know, time's pretty tight here. It's in the debugger, so I can't stop it. Okay. Let's see. So we'll type exploit. As I said, it's as easy as just typing exploit. We just find our program, edit, and all we do is we turn on arbitrary code guard that says no more marking pages as executable, a re-enable DEP, and then we hit apply. And now even if I use ROP to try and make this thing work, if I start that up, what we should find is that our really reliable exploit should now fail. So I've got my listener, I fire off the exploit, and we get no shell this time. Nothing's happened. The application has crashed. It's gone. And there'll actually be an entry in the event log, like this isn't it, but it'll say it would have been blocked from generating dynamic code, or actually it'll say it had been blocked from generating dynamic code. But in the interest of time, I just wanted to move forward and just show what we did there is arbitrary code guard can't fix the bug in that application. What's happening is the application's allocating a buffer, say 2,000 bytes, but we send in 3,000. And then it's passing that into the next function. That function is then trying to allocate that buffer onto a smaller amount of memory, and we're overriding the return address of the function. All of that doesn't matter in the terms of exploit guard, but what really matters is that we can't prevent the bug in the application. What we can prevent is anything horrible happening shortly after that. We use dep to stop the execution of that code that we're sending in as part of our string. And then we use arbitrary code guard to stop really advanced adversaries from using ROP to go and disable, or sorry, work around dep by enabling the execute bits on those things. Let me just show you one more example because it's a little more advanced for the people that are already super aware of dep. Let's use the same software and just quickly turn off the other controls so we don't step on each other. I'm not sure which order would happen, but just to be sure, we'll turn that off. We'll turn on this. So the application's running. I'm just going to send through another crash just to show you the difference. So similar, this is just another crash. You can see here, it's very similar, sending through 5,000 odd bytes to the gmon instruction instead. But this time, oh, that's not good. Oh, I forgot to put in the debugger. I'm on fire. Start the application, debugger attach. This time, what we should find is that it's not as straightforward from the adversary's point of view. So if I send that through, you can see that the application has crashed, sure enough. Here we go, access violation. But that address isn't like straight A's this time. We don't have, you know, an immediate override of the instruction pointer or something quite as useful. And you can see even here, the instruction pointer is not something that we've controlled input for, and neither is the stack pointer. If we were to jump to the top of the stack pointer like we did last time, we'd hit this and things wouldn't go well. This exploit's a little bit more clever in the sense that what we've managed to do, if we write a good exploit, is we're overriding a thing called the structured exception handler in Windows. This guy's designed to catch the process on the way down. So Windows allows you to register exception handlers that if your code doesn't handle the exception, Windows can do things for you. It might be writing the event log, taking a crash dump, could be a few different things. But you can see what's cool is that we've just overwritten that. So if we were able to carefully figure out an address where we could get to our arbitrary code again and start executing our malicious stuff, we've got a working exploit again in the same process with a different bug in that process. I'll just show you it works and then show you that exploit guard can help, and then we'll actually, it's number 4. We'll move on. Let's grab a handler. Oh, we have one. Oh, that's not great. Oh. You can see we get our shell again. So we have full code execution on that machine at this point. Let's quickly protect that application. So we just type exploit. We find our application, and down here there's a thing called structured exception handler overwrite protection. This just says if the structured exception handler wasn't there when the process started and someone's fiddled with it, that Windows should tell that application that things have gone horribly wrong and crash. So if I start a handler and I fire off the exploit again, we should find no shell and that the application has crashed. And I need to move quickly. I'm almost at time, but I just want to show you that what happened in this case is very similar. It's still a buffer. It's still a bug in the code. Exploit guard can't fix that. but exploit guard can say, like, there are particular behaviors that if we see inside a process on Windows, we should shut that process down because chances are things are going horribly wrong from a security perspective. And to give you an idea, there are tons of protections, and Chris Jackson wrote an amazing article recently that explains them much better than I can. But we looked at arbitrary code guard, we looked at DEP, we looked at SE hop. We spoke briefly about return-oriented programming, saying that if we notice inside a process that you're using particular APIs, that's probably a bad sign. But the point I'm trying to make is that you can just layer these on to processes that you're scared of, or that you need to worry about more. So not many processes are needing to load fonts from outside the Windows fonts directory, for example, or not many processes need to load an image from off the network or over the internet. And so they might be really easy controls that you could add to processes in your environment as well. The lessons learned, I just wanted to touch on really quickly. Audit mode, I said at the start, is amazing. I don't know if you caught it, but in the exploit guard UI, you can just click audit mode and it won't do the thing. It won't crash the process. It'll just write a Windows event if you hit something that looks a little bit sketchy in that process. But the problem I hit is that I applied that to the wrong control. I used that with arbitrary code guard on Slack at one point. And Slack's a just-in-time application. And so what that means is that Slack has behaviors that means it is generating arbitrary code all the time, all day. And I deployed that to our whole fleet thinking, you know, Slack's common, we need to protect it. Well, that was like about 1 million events into our WEF pipelines every hour inside the environment while I made that silly mistake. And the point I'm trying to get to is that the best approach is to apply this to a small number of machines first, really understand if the controls are working with the logging, and then go and deploy them a bit broader. Don't assume that you can't do any damage at all with audit mode, because I did. The other thing I'd say is don't overdo it. Don't think about your top 20 apps and go and apply exploit guard to your top 20 apps. Think instead about your apps that are at risk. So ones that are networked or that are written in non-memory safe languages, or ones where you don't get patches from the vendor very often. Like, think about your top 5 or 6 really scary apps, protect those first, get comfortable, and then look to expand exploit guard is the way I would approach it if I had my time again. The last point I wanted to make is just the group policy is a little odd. If you use group policy to apply this stuff, it's very easy. All you do is you type exploit again, you go into the UI that I showed you, and at the bottom, there's an export button. You export, and then you just tell group policy where to find that file that is your configuration file. If you ever need to remove that, you need to deploy a whole new file that just describes a baseline build. You can't just rip the policy out, is the point I'm trying to make. Anyway, I realized I went too fast, rambled a little, screwed up a bit. Please contact me over Twitter or on the chat if I can help with this stuff. I definitely don't know everything about it, but I spent a lot of time messing about with it, and I'd love to help if I can. Thank you very much.
Awesome, thank you. This is a topic near and dear to my heart, definitely. So yeah, there's some questions that are coming in. Like you stated, we did kind of run out of time. So I'm going to thank you once again for coming to BSides Toronto and giving your talk, and continue from there. Thank you.
Thanks, Max.